Hi everybody. We are going to start talking about exponential functions today. Our objective is to be able to identify and graph these exponential functions. Right now, just to kind of give you a heads up about everything I have, I printed out, if you haven't already, print out a copy of the guiding notes so you can follow along. Over here, I already have my graphing calculator open, which you should probably have with you or have one available on the desktop as we go through this. And we're going to get started. First thing before we get started is we need to look at some of the basic information of these exponential functions. And the first thing is just this general form, which is y equals a times b to the power of x plus c. It's called exponential because x is in the exponent's place. So exponential, x is the exponent. We have an a value, which if there isn't one there, it's going to be a is equal to 1. Our b value is the value that's being raised to that power of x, and c is whatever's being added at the end. However, if there's nothing being added at the end, our c value would be 0. The next thing we have is our y-intercept, which obviously is when x is equal to 0 like always, but here we have a little bit of a shortcut. If we can figure out what our a and our c value are, when we add them together, it gives us our y-intercept. The other interesting part about exponential functions is they have this thing called an asymptote. An asymptote is a line that the graph never passes, so it gets closer and closer to it, but it will never, ever, ever touch. And the reason for that is depending on what values we plug in for x, we'll never get it to equal 0, especially when we raise it to the power of b. So whenever it's an exponent, it will never get to 0. Even when the exponent of x is equal to 0, anything raised to the power of 0 is just 1, so it's not going to happen. So we just value it on whatever our c value is at the end. And then our range has to be greater than that value because the range talks about the function moving up and down. So it will continue to rise, however, it will not continue to fall because it's never going to go past that asymptote. So if there's nothing being added at the end, our asymptote would be equal to 0, so it would be right on the y-axis. So it's kind of hard to see sometimes, or not the y-axis, I'm sorry, the x-axis. Okay. So we need to go over a couple of things having to tell whether it's growth or decay. When it's growth, b is our growth vector, so depending on what our b value is, will tell us whether it's growing or decaying. In this terms, it's going to be growth, especially if it's greater than 1. So if the value being raised to the power of x is greater than 1, it's going to be growth, and our graph rises to the right. So what that will look like, we'll kind of make our graph appear. I'm going to make a pen. I'm going to take this, and it just kind of like starts low, and then it goes up to the right. So it looks something like this. And this side continues to get closer and closer to our asymptote. I'm just going to sketch in what an asymptote would look like. I'm just going to do a dashed line, because it's not an actual line on the graph, it's an imaginary line that the graph is never going to touch. And this is going to be y equals c. And then for decay, b is also our decay factor, but it's only when the value is between 0 and 1. So most of the time it's going to be a fraction or a decimal, but you might want to double check the fractions to make sure that it is less than 1. And then it's going to fall to the right, so the graph goes down to the right rather than up to the right. So it would look something like this. So it starts up high, and then it falls to the right, and it continues to go down as it gets closer and closer to wherever our asymptote is. And again, I'll just make my asymptote this x-axis. It just gets closer and closer. Obviously that bump wouldn't be there, it's just because of the way that this looks. So with these problems, we have to identify whether the following are exponential growth or decay. We're going to be looking at the b value in order to do that. So pause the tape or the recording, and we'll see what you think of all of them. Take about 10 seconds to do that. Alright, so we're going to get started. We have y equals 0.25 to the power of x. This is going to be decay because the number that's being raised to the power of x is between 0 and 1. That's our b value. Y equals 3 times 1/4 to the power of x is also going to be decay. Our a value is 3, but our b value is 1/4 because that's the part that's being raised to the power of x. Y equals 6 to the power of x is going to be growth because our b value is greater than 1. The a value is 1, so it's not there. then y equals 4 times 5 over 2 to the power of x. This is also going to be growth. Even though it's written as a fraction, 5 over 2 is 2.5, which is greater than 1. Okay, and we're going to start by graphing the following function, which is y equals 3 to the x, and this is when our graphing calculator over here is going to come in handy. We want to find the y-intercept, the domain, the range, and I also want to find the asymptote, which was written in later there. So the first thing I'm going to do is I'm going to create a table, and I'm going to make it from -2 to +2. So that way it's a centered graph. It always follows those steps. Over here is what I'm going to put each y value is equal to, but over on this side where it says y equals 3 to the power of x, I'm going to show all of the work for where I'm plugging things in, just so I can see that value that I'm plugging in. So this would be 3 to the power of -2, and since we have this exponent of a negative value, I have to move it to the denominator, like we're following our exponent property. So it'd be 1 over 3 to the second power, which would be 1/9. Take a couple of seconds or minutes, go through, pause the recording, see how good you do with it. Okay, so I plugged all the work in over here, and I already did 3 to the -1 power, and I said it was 1 over 3 to the first, which is 1/3. Then we have 3 to the power of 0, which is not 0, but 1, because it's a 0 exponent. 3 to the power of 1 is 3. 3 to the power of 2 is 9. The really awesome part about my graphing calculator is it will actually do these for me. If I go to y equals, I can type in the values into the calculator like we have in previous sections. I would do 3 raised to the power of x. You can look at the graph, and it has that exponential look about it. It looks like a growth, and I know it's going to be growth because our 3 was our b value and it's greater than 1. And if I hit second graph, it'll take me to the table, and I can make sure that my table values are right, which is so awesome. What I'm going to do is I'm going to go through and I'm going to graph these points on the graph. So I have a point at -2 and 1/9, so about right here. -1 and 1/3, so slightly higher. 0, 1, 1, 3, and 2, 9. It's really kind of hard for me to connect these, so I'm going to do the best I can, because the mouse just does not want to go for me. It's a little better. This one's just going to get closer and closer. And keep moving that way, and this one will keep going up. Right? As I continue going through these, our y-intercept is actually always going to be in the center of our table, and we do that because x is equal to 0 right here. It's going to be at 0, 1. Our calculator actually set off. Our domain, this graph is going to keep moving to the left, and it's going to keep moving to the right, but it's kind of just going up. But because it keeps moving to the left and right, our domain is all real numbers, so it's going to hit every x value. Our asymptote is when y is equal to c. And c is whatever is being added at the end right here. So this is actually plus 0. So our asymptote is going to be y equals 0. And it's important that we put y equals 0 because it's not just a number, it's a line. And it's a horizontal line which we're going to put on this graph, and I'm going to make it in red. That's actually where our x-axis is, like we talked about before. And the graph should never go beyond this point. Okay, and then we have our range. And since this graph is never going to go beyond this point, but it continues to go up, our range is going to be y is greater than 0, or y is greater than our c value, which we talked about on the previous page. Now we're done. We have our graph. We know what our y-intercept is. We know what our domain is. We know what our asymptote is. We know what our range is. Domain for any exponential function will be all real numbers. The range will depend on the asymptote. So I'm going to give you a couple minutes. Really just pause the recording and I'll fill this in as you go. We'll talk about it after. Alright, so we plugged in these values for the table off to the side where we would write everything out. We're going to use the graphing calculator to kind of help us with this one. So again, I'm going to hit second, graph. I know that at -2 my value is 9. I know that because 1/2 to the -2nd power is going to give me 4. 4 times 2 is 8, plus 1 is 9. If I put plug that in here, and I get 5, 3, 2, and 1.5. So we're going to use this, we're going to do the graph, and we're going to complete the answers. And again, I'll give you a couple seconds to fill it out, and just make sure you pause the recording. Alright, so we used the information we were given to complete the table, and then complete all the other information. This is our graph. Our y-intercept was at 0, 3. The domain was all real numbers. Our asymptote was y equals 1 because we were adding 1 right up here, which means our range is y is greater than 1. And there we have our graph. Okay, the last thing is that suppose a pond of fish doubles every week. So the pond starts with 4 fish. We need to write an exponential function of the number of fish per week. So the way that we're going to do this is we're going to say y is equal to, or however many fish we're going to have total. We're starting off with 4 fish. And it doubles every single week, so that means it's going to multiply by 2, depending on how many weeks go by. And we're going to multiply it by 2 however many times the weeks go by raising 2 to the power of x, since 2 is our rate. So for part B, it says how many fish will there be after 6 weeks, and x is our number of weeks. So we're going to say y equals 4 times 2 to the power of 6, since x is our number of weeks. We're just going to follow order of operations, so we're going to go clear out of this. We're going to do 2 to the power of 6, hit enter, and we get 64, and we're going to multiply that by 4. We get 256 fish, and we need to label our answer because it's a story problem. So we have 256 fish. And the other part is that we can also plug in for y, and it says how many weeks will it take to get 64 fish. So that means instead of plugging in for x, we're going to plug in the 64 for where y is. We have a couple of different ways of solving this, and the nicest way to do it is to actually just use our graphing calculator. Alright, so we're going to take this equation part, we're going to plug that into our calculator, and clear this one out. We're going to say 4 times 2 to the power of x, which is our equation. We're going to go to the table. That's a graph table. We're going to see where it's going to be equal to 64, so we keep scrolling down. You see at 4, it's equal to 64, so that means 4 is going to be equal to x. And x represents the number of weeks, so that means at 4 weeks, we will have 64 fish. Alright, and the last question is, how many days will it take for us to get 64 fish? We already figured out how many weeks, so the only thing that we actually have to do is take that number of weeks, which was 4, and multiply it by 7, because there's 7 days in a week, and we're going to get 28 days. Okay, so for more practice on exponential functions, you're going to want to do the exponential worksheet, and you're going to have to submit that. The answer key is there, so please make sure you check your work. Email me if you have any questions. Otherwise, that's about it. Hope you enjoyed.